So hello everyone, I am Rahadarman Nabid. Today we will discuss about a very important topic that is called longest common subsequence problem using dynamic programming. So this is a very important topic for your computer science background. So let's dive into the longest common subsequence problems and how we can solve it and what are the uses it. So so let's see the what is actually longest common subsequence problem. So we can shortly call it LCS. So in the book, there is a definition that is called the longest common subsequence. LCS is the longest subsequence that common to all given subsequence, provide that subsequence element are not required to occupy consecutive position within the original sequence. So this seems very hard to understand. Let me clear it out. So first of all, let's look at longest. What is longest? Longest is the highest, right? Longest is the long, is the big, right? That is what it means for longest. What is the common means there must be something to compare with two things, right? And what is subsequence? Subsequence come from the word sequence. So what is sequence? Sequence is, for example, you can see that S1 is B C D A C D. So what are the sequence, what are the subsequence are there? So B, only B is a subsequence. C, only C is a subsequence. D, only D is a subsequence. Another we can also call that BC is a subsequence, DA is a subsequence, or BCD or CDA. This is also a subsequence. So or we can also tell that BCDA. This is also a subsequence of these sequence. So we have to longest common subsequence is something that we have to compare with another subsequence, one other sequence, and we have to find out the longest subsequent that is common between them, right? And it's not have to be consecutive subsequence, but it have to be it have to follow some rules. So let's dive into some example to clarify it. For example, S1 is BCDAACD, and S2 is ACDBAC. So let's compare all those letters with one another. So A, so let's A, what is A? So the B is equal to A, no. C is equal to A, no. D is equal to A, no. So A is equal to A. So yeah, we found one element that is common between them. That is one subsequence. So let's entry it, right? So this is A. So after that, we have to go to the second element. What is it? C. So we have to find the rest of the element from S1, and we have to find out whether this is a common or not. So A equal to C. No, C equal to C. Yes, C is equal to C. So we have to enter it. So C is also also common between them. So we have to go to the D. D equal to D. Yes, we have to. So we have to enter it. So ACD is actually a subsequence, right? This is a subsequence. So anotherly, we'll another example. Let's say so C. For example, the second element C is same as this C, and D is same as this D. So we can say that. So let's actually go to the rest of the element B. So we'll find the B. No, there is no B. A. So there is no element B. So we have to. So we are taking the C and D as a subsequence. So C and D is a subsequence. So what are the length of this sequence? This length of this sequence is 3, and this sequence is 2, right? So the longest subsequence is what will be the longest subsequence that be common between them. So let's go to the third example, whether we'll find the longest or not. So let's go to the let's start from the C. Yes, C is here, so we'll enter it C, and then D. Yeah, D is equal to D, and then we'll go to the B. Is there any B? No, there is no B. So we'll go to the A. So yes, A equal to A and C equal to C. So there is a sequence common between them. So what is C, D, A, C? So this is a length of 4. There is no other longest common sequence between them. So we can call it the common longest subsequence. Let's go to the another example when these sequence are not being allowed or considered at a common subsequence. So A is equal to A. So let's say A equal to this number 4 position A. C is equal to, yes, this is a C, and D is equal to D. But we are actually breaking the law. So when we are comparing A with A, we have to maintain the sequence. We have to search for the sequence, rest of the element that we already compared. So we actually cannot compare the element we already compared. We have to take the rest of the element. So let's say A is actually compared to the fourth elements, it means that it already checked these elements. So we are breaking the rule, and we are actually going some elements, we are comparing some element that is already been compared. So this cannot be a sequence. So we have to maintain the sequence, and we have to find out the longest one to be the longest common subsequence. So how we can solve these longest subsequent common subsequence problems? So there are two ways we can solve this problem. First of all is brute force, that is recursive implementation, and another is dynamic programming. So in the brute force and recursive implementation, so we have to actually find out all the possible subsequence. So the number of possible different subsequence for a string will be the length ranging from 1 to n-1, and the total number of sequence will be 2 to the power n. So we can actually, if we find all the combination, for example, nc0 or plus nc1, nc2, we'll find after summing all those combination, we'll find that 2 to the power n number of subsequence are there. So a string of length n has a 2 to the power n-1 different possible subsequence if we ignore the sequence that has a length of 0. And the total time complexity for brute force approach will be um, big O of n into 2 to the power n, where is order of n will take the time to check if the subsequence is a common to both of the strings. So it feels that 2 to the power n number of combination that have to be find out by brute force, that is very time consuming, right? So that is the main problem to apply brute force to find out the longest common subsequence. So here is a pseudocode for solving this problem with brute force. So it says that if the last element and the two last element are not same, so we will not return, will return 0, right? So if anything matches, right, if any sequence or letter match between them, so what we have to do, we have to add 1, and we have to reduce the size of the sequence, right? So, and then if it doesn't match with one another, right, so what we have to do, we have to actually split it out by reducing one elements from each subsequence, right? So what it actually means. So for example, A, B, C, and A, so A, C, B, and A, B, C are the sequence. So we have to compare. So for example, we are compare with C and B. C is equal to B. No, C is not equal to B. So what we have to do, we have to reduce the length from each of the subsequence. So what will be the each of the subsequence? So we have will actually reduce from these sequence, that it will reduce to A and B, and A, C, B will remain the same. So, and then what we have to do, we have to compare with B and this B, last element from second sequence, and last element from the first sequence, and we have to compare it. Yes, this is actually matches with one another. What we have to do right now, we have to count 1. So what we have to do, we have to actually add that, yes, we found a common subsequence. That's why we are adding one thing. So 1. So then what we have to do, we have to reduce both of these. We have to remove B and B from both of the sequence and make it A, C, and A. So then what we have to do, we have to compare C and A. So what will be the result? Yes, that will not match. So again, we have to split into two different section, that this will be the A and A, another will be the AC, and this will be the reduce. So there will be nothing in here. So this will be the blank. So in this way, we have to split it down in another portion way. So that will be the AC and ABC. So if we split it, we'll find out some overlapping there. For example, we actually split A in here, in here also. So we are actually we are splitting the subsequence, single subsequence, several times. That is not very efficient for us. So after splitting, we'll find out the largest common subsequence, because we are actually adding if we found anything that matches between them. So from here, we'll come to a conclusion that there are two problems we'll find to imply the recursive algorithm in these problems. So first of all is the time complexity, and the second one is overlapping problem. So we discussed about time complexity, but to recap it, we'll say that the raw worst case time complexity of the above solution will be big O of 2 to the power n m plus n, where is m and n is the length of the string x and y. The worst case happens when there is no common subsequence present in x and y. So LCS will be 0. Each recursive call will end up 2 recursive calls. So it will actually split all the subsequence one by one. So that will take a long time, and the worst case will happen then. So another problem that I have shown in the previous slide, that we split a several times. So we don't need to actually split this subsequence several times. So that is called the overlapping problem. So LCS problem exhibits overlapping subproblem. So a subproblem is said to be have overlapping subproblem if recursive algorithm for problem solved is the same subproblem repeatedly rather than generated new subproblem. So this will make this algorithm to solve these long LCS problems so very time consuming. And so, so another one is the dynamic programming. So we can solve these LCS problem with dynamic programming. So what are the benefits of dynamic programming? First of all, dynamic programming, what is actually dynamic programming? So when the solution can be recursively described in terms of partial solution, we can store this partial solution to reuse that if necessary. So it's actually solve the overlapping problem that we have seen in brute force. So another thing it will benefit it, that is it reduces the time. So the time complexity for solving LCS using dynamic problem is a big O to the power m into n. So so if you see about the comparison, so it's actually drastically reduce the time. So it's very efficient to use the dynamic problem to solve LCS problem. So how we can solve this problem? So let's see that x is a sequence and y is a sequence. So we have to find out the longest subsequence. So at first we have to create a table of dimension m into n, where n and m are the x and y lengths respectively, and the first row and the first columns have to fill with 0. So what do we have to do? We have to make a row and make a column, and we have to what will be the size will be the n plus n. For example, this is for the x sequence. We have to make another extra column for it, and another one is the y sequence, and we have to make another column for it. So we have to fill out with the 0. This is the first step to solve this problem. So in the next step, what do we have to do? So we have to fill each cell of the table using the following logic. What will be the following logic? If the character corresponding to the current row and the current column are matching, then first fill the current cell by adding 1 to the diagonal element and point an arrow to the diagonal cell. So what actually it means? So for example, this is a C and this is A. So let's actually compare with both of these sequence with this A. So let's see. These are the 0 from first. So we have to go to in this way, and so this is the first position. We'll compare with C and A. C is equal to A. No, that is not A. So if that is not match, so we have to get the value from this and these top value and the left value. We have to take the highest value from here. So there is no highest value. 0 is the highest value. So we will actually assign it 0, and we have to make an arrow in any of the direction, because those are same, right? So any position is same. So we are making an arrow direction. So in the second, so if we compare with B and A, it is also for a same that it doesn't match. So we have to take the value from here and here. So in the top and the left side. So both of them are 0. So we'll assign it 0, and then we'll go to the next element, that A and D, these are the same. So and then we have to go to last element. Yes, we'll find out that A is equal to A. So what we have to do, we will not take the maximum value from the top element or the left element. We have to take the value from the diagonal element. We have to diagonal element. What is the value of the diagonal element? So that is 0. So we have to add 1 with 0, because we find a sequence that matches, right? So that's why this is 1, and we also actually make a point to its diagonal element. So this is the first set. In this way, we have to fill out these C for C value, A value, D value, and B. So let's see what's happened. So in this way, actually, else, so let's go to these information, that else take the maximum value from the previous column and previous row and element to fill the current cell, point out the arrow, cell in the maximum value. If they're equal, point any of them. So what I mentioned, that we have to take these top position value and the left position value if C is not matched with them. So if we found any match with them, we have to take the diagonal value and add with 1. So let's go to the second value, that c is equal to the c. So we have to take what value? These diagonal value. So this diagonal value is 0, so we have to add 1 with it, so it will be 1. And then for the next element, c, we'll compare c with b. B is equal to c. No, this is not c, is not same. So what we have to do, we have to take this value and this value, we have to compare which is the highest one. So this is the highest one, right? This is the left value is the highest one. So we have to take these value to assign in this position, and we have to take we have to point out that this value comes from here. So in this way, we will point out the another next value and the next value, right? So let's go to the third element, right? So this is a, so we have to compare with c. Is matches? No, it's not matching, right? So we have to take the highest value from the top and the left part of the element. So we'll find 1, so we'll have to assign with 1, and then we'll go to the next element. After, in the last element, we'll find that a matches with a, so we have to take the diagonal element and we have to add 1 with it, so it will be 2. In this way, we have to fill out all the values in this matrix. So what it says here, that the value in the last row and the last column is the length of the longest subsequence problem. So in the last position, we'll see that is 2. This will be the longest subsequence problem. So in this sequence and in this sequence, that common subsequence problem's length will be 2. That is our answer. So what if we want the sequence from these matrix? So that's why we have to make a pointer to find out the sequence. For example, in here, we'll see that we indicate that this pointer points out these 2. So we have to follow this pointer to the 2 element. Then we have to again point out, we have to follow the pointer in this position. So when we'll find any diagonal pointer, we have to take the value from the matrix. So what is the value? So it is a and a. It means that when any diagonal pointer value found, it means that there is a common sequence, there is a common letter between them. So we have to capture this, we have to save it. So what will be? This is a, right? This is a, e is common. So then we will go to the pointer values that has been indicated. So we'll check if there is any diagonal pointers are there. So there is no diagonal pointer, so we have to follow the pointer location, and then we follow the pointer location. After that, if we come here, we'll see that there is a diagonal pointer has been pointing towards. So we have to take those values. That is, what is the value? That is c. So we have to take the value. So we'll have to assign those value. The previous one is a and another one is c. So this is the ca is the longest subsequence of the problem. So if we go to the another way, we'll see that from here we can also go to the left side. After going to left side, we'll see that there is another diagonal pointer pointing out, right? So we have to capture that. So what will be that? This is actually b, and another one. So we have to go to the a location. If we go to the top position, we'll find another another sequence. So there will be another sequence we'll find. So there may be a lots of common subsequences are there, but we have to take the longest one. So this is the implementation of longest subsequence problem using dynamic programming. So let's go to the pseudocode. So what we have done so far, we have to take the length of a sequence. We have to take another length of the sequence y. So after that, we have to make a matrix. After creating the matrix, what we have to do, we have to compare each value and fill out the table. We have to fill out the table. If any things have been found that matches with 2 sequence, we have to take the diagonal value adding by 1. And if if there is no common sequence, so what we have to do, we have to take the highest value from the top element or left element. And after that, after going to the last position, we will return the the value last elements, right? That we have found in the matrix in the last element. So what is the application of this longest common subsequence? There is a lot of application out there. First of all, is a comparison of genome subsequence of data. If we compare between 2 genome data, so we can use this longest subsequence problem. So another thing, we can authenticate user within their mobile phones through in-ear signature. That is also a application for longest common subsequence. We most of us, we are using Git. So revision control systems such as Git and reconciling multiple changes that also been identified by these longest common subsequence and text analyzing, pattern recon, file compression. These all the things has been can be done with longest common subsequence. So in fact, efficient tree matching, biological application of LCS and similarity measurements are varied from sequence alignment in comparative genomics, polygenetic construction and analysis to rapid search in huge biological subsequence, and compression and efficient storage in rapidly expanding genomic dataset, and resequencing a set of strain given a target strain is an important step in efficient genome assembly, are the main application of longest common subsequence.